Okay, so sort of summarizing what we just described, right? The graded potential is initiated by a stimulus, which is coming in from another neuron. It is a small change in the membrane potential. It is magnitude varying, so the magnitude of it can vary. It can be a 10 millivolt change, a 15 millivolt change. It can depend, right? It can be graded. That's why we call it a graded potential. An action potential is always going to be positive 30, then back down to rest. So it's not graded. It's all or nothing. A graded potential can vary. It can be a smaller change. It can be a medium change. It can be a negative or positive change as well. The spread of a graded potential happens by electrotonic conduction, which means that the change in the channels that are opened, right, the amount of ions, that are being conducted through the membrane can change the membrane potential, and that can allow this graded potential to spread, but not very far, only across the soma or cell body. And then the graded potentials are what we describe as being decremental. So the magnitude is not going to be sustained. It's going to actually dissipate the farther away it goes from the original stimulus. So here's the point of original stimulus. Notice the strength or magnitude of this potential is slowly decreasing, right? This is what we mean by decremental. It's going to decay or basically dissipate or fizzle out as it gets to the axon hillock. And so if at the axon hillock it's still strong enough, then we're going to generate an action potential. If not, we simply lose that graded potential altogether. So the graded potential has the ability to become an action potential only if it is strong enough by the time it gets to the axon hillock. Someone's asking, does the action potential bring it back to resting, or does it continue with more? So an action potential must always go up to positive 30 and back down to rest. That's always going to happen. It's never going to change in magnitude. It's not, but you can't have a big action potential or a small action potential. It's an all or nothing phenomenon, and they are exactly identical, all action potentials. Okay, really good question. And we will reiterate that some more as we go along. All right. Okay, so notice here we have a small change in the membrane potential. So this is one graded potential. Notice down here we have a stronger change. This is what we mean by this being graded. There can be different types or different gradations or variations in the magnitude of that membrane potential change. The purpose of graded potentials is to get us to threshold. So the threshold we said was negative 55. It is the membrane potential requirement to generate an action potential. And so graded potentials help us determine whether or not we have enough of a membrane potential change to actually stimulate an action potential. Now, there can be different, as you said, different types of graded potentials. They can be hyperpolarizing, which are negative changes. This is where the membrane potential becomes more negative or goes below negative 70, or more commonly and more favorable to become an action potential is if they are depolarizing. So this is where the change is a positive change. It actually excites the membrane. So it's going to be an increase in that value. So it's going to go from negative 70 to negative 60, right, to negative 55, and then we can fire an action potential. So there are different directions in the membrane potential change. Therefore, there are different types of graded potentials, but only the depolarizing graded potentials get us closer to threshold, which get us closer to an action potential. We can also think about summation. So summation can happen temporal summation, which is the same stimulus repeated close together in time. In other words, it's on the same spot on the cell, right, the same location. So let's say we looked at one specific area where one neuron was synapsing and it stimulated one graded potential, which we can see here, stimulated again another graded potential. That was enough to get us to negative 55, and so we can have an action potential. So that is temporal summation. It's the same spot on the neuron that's receiving stimuli that are close together in time, right? Repeated one after the other. Additionally, we can have spatial summation. So these are different stimuli, different spots on that cell body. And if they are happening at the same exact time, that can also be added together by spatial summation. So notice here we have a positive membrane potential change or a depolarizing weighted potential. And then we also have a hyperpolarizing weighted potential, both happening at the exact same time, but on different spots, right? Different spots on the neuron. These can be added together. And because this one was positive and this one was negative, they cancel out, right? They both cancel out. So graded potentials have the ability to sum or to be cumulative or to be added together. It can be temporal summation, same spot on the neuron, just difference in the time, right? They're coming one after the other. Or spatial summation, different spots on the neuron, all coming in at the exact same time. They overlap in the time. Okay, let's look at this checkpoint question. Why are graded potentials unable to communicate over long distances? Why are graded potentials unable to communicate over long distances? So who can recall why this is? All right, they don't have enough magnitude. Excellent, excellent, and well said. So they don't have enough magnitude. They are not strong enough. Okay, they are very small changes. They're also not sustainable, right? So even if it's a small change and it's cumulative, which we know via summation, it's not going to stay the same. It's going to dissipate the further away it travels. Action potentials don't. So as an action potential goes ripping down the length of the axon, it's going to be sustained. Its magnitude is going to be sustained. Graded potential, not so much. The further away from the stimuli it moves, the less and less the magnitude is until it dissipates. So it's not able to travel along or across longer distances. All right, perfect. Let's move on to lecture objective 2. We've got about 10 minutes here, so we're going to just go ahead and start that. This is to explain the ionic basis of an action potential. In other words, what ions are moving and in what direction to bring about an action potential. And then we're going to go on further to describe the gating mechanisms for voltage-gated sodium and potassium channels. Okay, so earlier we talked about channels being ligand gated versus voltage gated. We're going to describe exactly what those mean. We talked about where on the neuron we can find those different channels, but we're going to talk about what it means. They're both gated. In other words, there's going to be a certain requirement or a certain condition that must be met to open that channel, but one is going to be a ligand, and that is something binding to it. The other is going to be a voltage, and that is going to be a specific value for the membrane potential. Okay, so we'll talk about what those conditions are as far as the gating mechanisms. So as we think about the membrane potential changing, we can talk about the resting potential, which we have described. We have talked about a decreasing or negative change, which is a hyperpolarization or hyperpolarizing event. Or we have the opposite, which is a depolarizing, which is a positive change, right? And then we have a repolarizing, which is where we reset to rest from a depolarizing event, okay? So while we think about these events, we want to recall what's actually happening, right? We talked about the equilibrium potential for sodium. Who can recall the value of that? What's the number of sodium's equilibrium potential? Not 94. 94 is for potassium, right? So 94 was negative 94, that is, was for potassium. Okay. What about sodium? Sodium is going to be the opposite direction. It's going to be positive, but what was the value? Can anyone recall? So down here, way down here is where we have potassium's equilibrium potential. This is -94. And then way up here, we have sodium's equilibrium potential, which was 60. Excellent. Yes, it's going to be positive 60, which is really high up in terms of the membrane potential change. We talked about the fact that the distance away from rest, right, that sodium's equilibrium potential is really a reflection of the force, the magnitude or strength with which sodium wants to move, right? And the same is true for potassium. The further away we are from the equilibrium potential of that ion is the stronger that ion is going to want to move. So potassium has a weak magnitude or strength to move when the cell is at rest, simply because it's really close. It's close to the resting membrane potential. While the cell is at rest, sodium has a much stronger urge to move because it's really far away from its equilibrium potential when it is at rest. Okay, so that's kind of the baseline as far as describing the membrane potential values here. So when we begin to depolarize the cell, we're really just changing the membrane potential of that cell. We go from -70, it starts to become more positive, more positive, more positive. At its peak, it's going to be +30. It's never going to actually reach sodium's equilibrium potential, because by the time it gets to +30, some other channels are going to open up. That is potassium channels. And that is going to result in the opposite direction of movement of the membrane potential, right? And now that we are at +30, potassium is going to really want to move because we're further away from potassium's equilibrium potential. So as soon as those potassium channels open up, potassium goes rushing out of the cell, and that is what allows us to repolarize back down to rest. Okay, so as we speak about these events, we're going to be using terms like depolarized, repolarized, and hyperpolarized, but I want you to be thinking about what's happening as far as the values, as far as these membrane potential values and the direction of change. Okay, let's speak about the channels we have here. And I think this is where we end off for today, but let's describe these channels a little bit more. So we've got leak channels on the membrane. These are always on the membrane, always open. They're found all over the neuron. They are usually what bring about the resting membrane potential. So if you remember us talking about potassium being more permeable, having more channels, these are the types of channels we refer to when we talk about that permeability or that leaking of potassium. Same thing for sodium. The ligand-gated channels are going to be open or closed depending on the ligand. And a ligand is any type of molecule that can bind to a receptor and bring about a change. So ligand-gated channels are only found on the dendrites and the cell body of the neuron, and they will open and close depending on what is bound to that channel. In other words, the channel is also acting as a receptor to bind something. For voltage-gated channels, it's going to open or close depending on the membrane potential. So if the membrane potential is -70, certain channels are closed. As the membrane potential becomes more and more positive, let's say when it gets to +30, other channels will open up. So the conditional requirements to open or close these voltage-gated channels is a change in the membrane potential value. Okay, that's why it's so important to remember those values as we go on when we talk about these depolarizing and hyperpolarizing changes. All right, these voltage-gated channels are found throughout in general, but they are more concentrated along the axon, specifically along the axon hillock. If you remember us talking about the hillock being the area where we're really measuring whether or not we have reached that threshold value, there's going to be a lot of these voltage-gated channels here to help trigger the action potential if we do, in fact, reach that threshold value. That's why they're found more concentrated at the hillock. Okay, so really important about the voltage-gated channels is they are going to determine whether or not we meet the requirements, and then they are going to be responsible for initiating or triggering the action potential, right? So these are really important. Lastly are the calcium channels. They're going to be at the end or the axon terminal. They're going to be responsible for releasing certain neurotransmitters, and these neurotransmitters are going to bind to the adjacent cell, and this process is going to start all over again on the adjacent neuron. So this is where the electrical signal, that is the action potential, is converted into a chemical signal, that is a neurotransmitter or a chemical, sent across the synapse to another neuron, and then that can result in another electrical signal. All right, so that is basically how we have different channels along the neuron that are responsible for different aspects of the action potential. Okay,